It's getting a little chilly here in North Carolina as fall is essentially beginning. In this class, we're going to continue our theoretical physics week and see one of the most beautiful connections in the history of physics, and that is the discovery that light is an electromagnetic wave. And this is going to be done with a theoretical derivation. Now, there are several ways to handle this. We're going to use a simpler form of the Maxwell equations, one which you have seen in introductory physics, and save the differential form, the more advanced form, for electromagnetic theory, which is another course you'll be taking. So I hope you enjoy this week of theoretical physics, where the emphasis is on mathematical physics using physics and calculations. I'm also going to show you a review of your electricity and magnetism from the introductory physics class with calculus. So hopefully, you will recall everything in terms of the Maxwell equations from that class. And in the spirit of theoretical physics, I'm going to show you where things come from and try to derive as much as I can. And even though the derivations are not going to be 100% derivations, because we're using experimental discovery for some of these equations, I will take a theoretical physics slant when I present the material. Okay, let's get started. Chapter M, EM, electromagnetic waves, and light speed, or the speed of light. And the first thing that we're going to do is talk about the wave equation. So we know when we have a wave equation with E and M waves. In search of a wave equation. This is one of the classes I actually remember from my undergraduate days. For some reason, this class stood out. This wave equation is fascinating. So here, we know that we have, say, here's a wave, psi, x, and t. And if we're moving to the right, it's going to be a function of x minus vt. So let's let u equal x minus vt. Now we're in search of a differential equation of which the solution is some general function with the argument x minus vt. So what we will do is we will look at some partials. The partial of u with respect to x is 1, that's going to be handy. And the partial of u with respect to t is minus v. So in search of our differential equation, let's take the partial derivative of psi with respect to x. Now, here what we're going to do is look at the f function to help us. And since the f function is a function of u, we'll say take the regular derivative of f with respect to u, and then the partial of u with respect to x, using the chain rule. Now the derivative of u with respect to x is 1, so this is going to be df du. All right, that's what we get. If we take the partial derivative of psi with respect to t, then we want the partial derivative of f with respect to t, and we set it up the same way. Take the regular derivative of f with respect to u, and then the partial of u with respect to t. Now, the partial of u with respect to t is that minus v, so this is going to be minus v df du. Now, I can construct a wave equation from these two by simply saying that if I put the pieces together, for example, the partial of psi with respect to x, this thing, if I divide by negative 1 over v on this thing here, I have my differential equation. All right, so let's look at this again. The partial of psi with respect to x is df du. The partial of psi with respect to t is df du with this extra minus v in front of it. So if I divide by that minus v in front of it, then I will make this side equal to the left side. So both of these sides now are going to be equal to df du. Now we have one problem, and that is if we look at a wave going in the opposite direction, say where v changes the sign, then I would have, let's go ahead and write this out. This is a wave traveling to the right is the 1 over v with the minus sign, partial, the wave traveling to the right. But then if I have a wave traveling to the left, that v is going to change. I'll have a plus 1 over v. Now you can see that very easily by just switching the sign of the velocity. You might recall we looked at a g function, say x plus vt, as a wave moving to the left. So if you did this whole thing again with the v is plus, you would just be flipping the sign. So this is bad. Two differential equations, one for the traveling to the right, one traveling to the left, not good. So what do? Well, we could look for another derivative. In fact, from mathematics, we know that if you have two independent solutions, the differential equation is a second order. Just like an analogy with algebra, if you have a quadratic equation, you have two solutions in general. And there's solutions like x would be f or x, and you have ax squared plus bx plus c is 0. And here, when you have the differential equation, we'll get two functions. So if we continue to take the derivative again, all right, so we're going to go back to this step. And here, if we go back just to this step and take the derivative again, then the second derivative with respect to x, I would then come in here and I want a partial derivative of x on the df du. And that would be then the second derivative with respect to u, and then the chain rule again. But remember, du dx is 1, so this is simply the second derivative. Now, if we do the same thing, and we're working with the right wave here, we're working with this general right situation. So if we take the derivative with respect to time, we then want the partial time. And here's same idea, the chain rule. There's your second derivative, but now the partial of f with respect to t, that's going to get you that minus v. Another minus v is going to pop into place there. So here we are looking at, let's see, we dropped something. Let's just go back for a second. We dropped when we have the second derivative, there's a minus v in here, so we need to put that back. We need to put that in, minus v. And there is still that minus v here. That came from over here. When I took the second derivative with respect to time, I need to have that minus v in the front. Then I work on whatever's left. So I just happen to have missed that first time going through. Happens all the time. Don't worry about it. It happens. I'm sure it happens to all of us. And then here, if you do that, this part here is another minus v. So now minus v times minus v, this is going to get you a v squared. So now when we set the equation up, we need to divide the second one by the v squared. Let's do that. You got the second derivative with respect to x equals 1 over v squared so we took this time case divided by the v squared so that it looks the same as the x case. So this is here the wave equation. Now, my mentor at University of Maryland had a cool way of remembering this. He basically said distance, like x, is velocity times time. So that means when you have the x, a meter squared down here, or just think x is vt. So in other words, to make the units come out, forget that they're squared for now. Just look at this relation here. X is vt. So the v has to go with the t. Okay, so now we're going to go and do a little detour because we need to understand electricity and magnetism, since light is going to be shown to be an electromagnetic wave. So we first of all look at Gauss's law. We're going to look at the Maxwell Equations. There's 4 of them. And the first one involves Coulomb's law. Now you may have remembered this Coulomb's law, and I like Coulomb's law very much because it's the same form as gravity, Newton's law of gravity. So you're looking at this relationship where the constant here in the MKS units 1 over 4 pi epsilon naught. And if you remember gravity, the gravity case, you had a big G for the constant and a big M and a little m over r squared, the inverse square law. That's Newton's law of universal gravitation. So here you would have mass could be the moon, this is the earth, or this could be the sun, this could be the earth. And r is the distance from the centers. And this is your force equation. And this is going to be attractive and equal and opposite. So the same force pulling on either body. Then if you look at, say, Q and little q, same idea with the r, then this is similar law, although here if the 2 q's are positive or negative, that's going to be a repulsive force, and if one is plus and one is negative, that'll be attractive. So it could be either case. So what they do then, you might remember, they write down F equals mg. They let the g be everything else. So g is going to be everything else. What am I doing? Everything else is here. Okay, so that's going to be the big G m over r squared. And if you do the same thing with the electric field, and we'll call that E, everything else would be, take that Q out. In other words, you want the case where the force is the electric field, times the Q, or, this becomes the Q, and this becomes the E. So Q times E, E times Q, all right? Then you would have here K, big Q, over R squared. And the Gauss's law is a very, very interesting way of looking at this. What you do is you consider the charge Q, big Q, and then make a sphere around it. And that sphere, see the force or the electric field, this is like the force per unit charge, little q. This is going to be the same all the way around. And since the surface area is 4 pi r squared, if you do this kind of a multiplication, E times 4 pi r squared, that's going to get you K Q and then you're going to have here a 4 pi. So we're going to write this in a fancy way. It looks a little scary, but it's not. If you take the electric field and make a dot product with a patch of area, so you could just think of a patch of area there, a little dA, and you can make it a vector, and it's going to be R, and you can make it a vector where we'll put like a little, you can have a little n hat dA, and since it's from the center, the n hat is often just given as an r hat like that. So if you do this, then the electric field, which is k q over r squared, r hat, where r hat points away from the center, then when you make a dot product with the area like this, 2 unit vectors, when you dot them, going to be 1. And then here, you can do the integral very easily because there's a constant at the distance r, so that you'll integrate, when you integrate this over the surface, that's where, the kq over r squared hangs around, and then you get the 4 pi r squared for the area integrates. And when you do that, see the r's cancel, and the k is 1 over 4 pi epsilon naught, and the q is hanging around, and there's a 4 pi from over here. They cancel, and you get this cool formula, q over epsilon naught. And then you could write down this law that if you do this surface integral, you get big Q over epsilon naught, and Q is inside that sphere. See? That's the first Maxwell equation. So this, hopefully you saw in your introductory physics course, because in the second semester they do this. So I want to give you a review here in the style of theoretical physics. We want to kind of show you a lot of things rather than looking things up. So we did that. And then the second Maxwell equation is the one with the magnetic force. And these are fundamental forces in nature. Fundamental force of gravity, fundamental force of the electric force. And see, it was inspiring Einstein when we at first had 2 forces for the gravity. Before we knew gravity was universal, we had the law for the heavens and the law for the celestial and terrestrial, and that got unified. We're going to see today that magnetic and electric forces are unified, and Einstein gave us the concept of the unified field theory, where he wanted to bring gravity together with the laws of E and M, which is what we're doing here. So these are fundamental force laws. So the magnetic force, you might recall here from your physics that if you have a current going in a wire like this, that there is a force field, and you could use your right thumb going up, and it curves this way, sets up a magnetic field. And just like here, you had some kind of interaction with the charge, Q times the E force field. The way this one works is you have the charge, it has to be moving, and you take V cross B, and that gets you the force. So if you have a charge, a point charge, say here, Q, moving upward, then when you take the B, what they do in books often, they'll put the little X, which means the B is going into the page. And this is your, say, velocity direction. So if you go into the page and have the V cross B, what you do is the right-hand rule, you basically point your thumb into the V direction, and then the way I like to look at this is like you take a screwdriver, for example, and if you have like 2 vectors, say A and B, if you want A cross B, you turn you have to get behind the page and turn A into B. Let's do it. Let's make it a little simpler. So you have A here and you have B, going down like this. Then if you take the screwdriver and turn clockwise, like this, like down like this, then A goes into B. All right. So here, if you have the current, say, going like this, I going this way, and that means the magnetic field is like this, and I'm going to say X points into the page, and if your velocity is like this is pointing down. So that means if that's pointing down, maybe do it like this. If that's pointing down and V is like here, if I take the screwdriver and turn V into B, the screwdriver advances toward the wire. So this is the force that a plus charge goes through the wire. Now it's very fascinating with this fundamental law that you can take, Coulomb's law is fundamental and the magnetic force law is fundamental. But if you take special relativity and look at this and say you have, say, the wire and the electrons, say electrons are moving this way, if the current, the positive current's going the other way, with special relativity and Coulomb's law, I can show you magnetic force is going to be present. If you have a charge here, charge sees nothing because there's just as many positives as negatives. But if you should travel with a velocity v, then since you have Lorentz contraction effects, which you learn in relativity, since the electrons are moving the other way, there's more, relative velocity for them. They contract more, and you see here more negative, and plus wants to go to the negative. I have a short video that you can watch that it talks about that. That's a very, very fascinating fascinating idea. If you go to the notes here, there's a 10-minute YouTube video where I describe the derivation. So in that sense, we could say we start with Coulomb's law and special relativity, and I'm going to continue in that fashion, show you where I can sort of almost derive the Maxwell equations. So here we're going to look at, that's Ampere's law, by the way, with the current. And here we got some individuals. We got Coulomb, all decked out in his uniform. And we got Gauss, and we have Ampere. All right. So now we go to the next law, which is the law of Faraday. So it's Faraday's law. And here's what you learned in your introductory physics class. So let's go ahead and make a new heading, M3. Then we'll call this Faraday's law. So I've kind of numbered, when you get to 4, we'll be finished, 4 Maxwell equations. Faraday's law. And this is what we learned, that E dot dl, and this is one dimension, this is the loop integral, is minus the magnetic flux, see derivative here. All right, so let's see how we might get this, because we're theoretical physicists this week, remember? So here, if we have a magnetic field that's into the page, so this is your B field going into the page, all this here, going into the page, and we're going to have a wire, rectangular wire, and we're going to pull. So we're going to pull it, and we're going to look at 3, 4. Let's look at 4 charges, and these charges Q. Here's a Q, and here's a Q, and here's a Q. Now, when you have, your force law here, F is Q, V cross V. Then here, since we're moving to the right, this is the V. Then if we take the V and cross it in with that X, you're going to be going up. All right, so you have, you know, the V going this way, you have the X going into the page, and then if you take the V cross like that, you're advancing upward. Now, these charges, see, want to pop off, but they're not. They're in the wire, and they want to pop off, so there's no current there. This one is outside the magnetic field, so nothing here, but see, this one starts to move up. Well, if that happens, then we're talking current. We're getting some current here. But when we look at this, let's say if we have this distance L, all right, and we have some width, length and width, that the velocity is, as the velocity goes like that to the right, then notice this L decreases, so the velocity is negative dl dt, all right? Because this region here is going to get smaller and smaller as you pull out, and finally L is going to be zero, like when you leave. So we have the force, which is Q VB from the force law. Notice that the magnetic field is perpendicular, so when you use this product, cross product, remember that's VB from your introductory class. That's the sine of the angle. If the angle is 90, you're going to get 1. But see, this is now acting like I'm feeling this force upward. This is acting like an electric field, pulling me up. I'm getting the electric field effect. So in that sense, this effective electric field that I'm feeling, this charged field that makes it go up, is V times B. But what is V? V is negative dl dt. So if I look at this, I could write this as minus dl dt. Let's just go ahead and leave it like that. And then here, if I look at, just curious, like what is this? If I take this, for example, this loop integral, let's just go ahead and look at this, see what this is for fun. And if I look at that, and let's go around where if you put your thumb straight in, your fingers curve that way. Let's do the loop that way to match the magnetic field direction with the thumb. Then this says take the electric field and dot it with the L. Well, the electric field is going to be up. Here, L goes to the right, and you take a dot product that's perpendicular, you get 0. This is the only one you're going to get. So that's going to be E times the width. So if E times the width, and if I go to put these two together, E times the width is minus dl dt WB. And then I'm going to go ahead and put this derivative and put the L WB on the inside. You could imagine W changing. However, we're making a big jump here when we say, what about B changing? Well, it turns out this is a true equation. So this is not a rigorous derivation because you really have experiment that brought about these laws. But look, this is it. I got the flux here. This is the definition of flux. This is the area times the magnetic field. That's what flux is. So that's minus d dt, and that's the magnetic flux. So I kind of derived it, or at least I showed you it's plausible where that equation would come from. So now we look at a summary. If we look at a summary here, which we already have these equations written down. Now, the only one I didn't do for you is this one. So let me go ahead and fix that. In other words, this is coming from your introductory physics class, where we're talking about the magnetic force law. Here I'm going to use little I for the current. And this is what you find in your course. You find this formula, all right? And then there's a vector that they might actually call that like a theta hat, since when you have the current going like this, it goes around, it's an angular. So what I wanted to do here is show you that if I went around that circumference, I would have B 2 pi r, distance r away from the wire, and that would be mu I. And then if I looked at this as an integral of that magnetic field going around that loop, I would get this equation because the circumference is 2 pi r. So that's the form we want over here for a Maxwell equation. And this is called the Lorentz force of Lorentz transformation fame, where you have both fields present. And this is what we have so far.
Oops, I forgot about one of the Maxwell equations. Let's go ahead and fix that right now. And that is the one that's analogous to this Maxwell equation, where instead of having E, we have B. Now you might recall that we swallowed up the charge completely with the sphere. And if I were to swallow up, say here, a region, you see that the magnetic field's always going to be circular inside, never to pierce outward. So this is a piercing outward effect. It's not going to happen with the magnetic field. So that means we're going to get zero. We're going to get zero, see? So we need to add that as one of the equations, that the magnetic field lines are circular, see, when you have the wire, for example, and you get a contribution when you go around a circumference along the circle. But if you take an area to, let's say, incorporate magnetic field lines, since they all remain inside your sphere, they don't pierce out, you get zero. And that's also saying that there's no such thing as a magnetic monopole, see, because this is a charge, like a plus and a minus. But see, with the magnet, you get a north and south pole together. In magnets, you cut a magnet in half, you still get a north and south pole. So that's a very elegant way to say there are no magnetic monopoles, although folks have been searching for them for many, many years. If one is found, of course, that's Nobel Prize material. But so far, we have not found any, and this equation stands as it is.
Now, Maxwell added a piece to this that is very, very important, because you don't have light existing with just these. And the Maxwell equations, when he did them, he had, I think, like over 20 maybe, or over a dozen. And I'm showing you now the modern formulation. Heaviside played a role in that to get the equations elegantly down into 4. So when they're vector equations, you can collapse them down. So that's what we're doing. So M4, Maxwell's equation. So hopefully all of this you have seen before in your introductory physics class. So this is a nice summary of the landscape. There's James Clerk Maxwell right there. And to show you the Maxwell piece, rather than just write it down from the introductory physics class, let me show you. We're going to look at a capacitor which has, 2 plates like this. And you have like a plus charge and a minus charge situation. So we're going to need the electric field near these plates. Now you've done this also. I'm going to do it again for you. This is where you set up Gauss's law and you make a little pillbox. You make a little box, and this goes underneath here. And then when you have like all these plus charges here, you're going to have electric field that's going to go up, and then on the bottom it's going to go down. So if you have a test charge that's positive, it's going to chase you away. So then if you do the Gauss's law, E dot dA is Q on the inside the Q on the inside here would be, if this is an area A, that would simply be the density. This is the charge density, the charge per unit area. That's all that is. And then here you would have on the top, the normal points up and the bottom, the normal points down, but the E field is lined up with those. So remember, your area is going to be a dA with some unit vector. So if you have a patch here, that's going to be up for the top one, you see. And that's going to get you then an EA. And then on the bottom, since they line up, it's going to get you the same thing. So you find out here that 2EA is equal to this. The A's are going to cancel. And you get E is sigma over 2 epsilon. Now, this would be like an infinite plane of charge, or you're toward the center. Edges are far away. So we need that in our next step. And then we go to look at, say, the two plates. We turn them, orient them edgewise. And we have a current we're sending in, making plus charges go more here, chasing them away over on this side. And remember, your electric field points away from the plus. So here's an electric field set up. And since that's due to two plates, that's going to be a magnitude that's going to be sigma over epsilon naught, because we got two plates that reinforce each other. So you double this. So the question is, over here I have a magnetic field that's set up, as we know from the previous discussion. The question is there a magnetic field set up in here when there's no current? That's what we're going to investigate. So if we look at the flux by definition is the field strength, times the area. And so the field strength here would be E, and the area, we'll take a little patch of area for our discussion. So just imagine a little area, edgewise like this. So we got to turn it, like that. It's piercing through. And that would be here, the area is not going to change. So this is going to be the derivative of the electric field with respect to time times A. But what is that E? Well, that's this thing. So that means I'm going to have, let's get the constants together. I have a constant A, I have a 2 epsilon naught. I'm going to have a D sigma D dt, because see, density's changing. I'm putting more charge on there. Okay, so this is A over 2 epsilon naught, but that sigma, remember that sigma, is going to be equal to the charge per area, all right? So that means here I'm going to be looking at d dt of q, and it would be a 1 over area's constant. These areas cancel, and made a mistake. This E, I forgot to double it. So there's a 2 here, and there's a 2 there, all right? Because remember, we have two plates, all right? And when I pulled this down from there, I'm gonna have to maybe say 2 times, so that when you're using the one plate formula, you wanna double it, because you have 2 plates reinforcing. Test charge is gonna be kicked from here, but pulled, up to the right. So this is nice, because then the 2's cancel, the 8's cancel, and I get here, this is I, and I just simply get I over epsilon naught. So the question here is, this is like an effective I that's in that space, epsilon naught. So it suggests, when I have the Ampere's law, it suggests that this I should be added to this other I. So if we do that, we would then have plus mu naught epsilon naught, the change of the flux with respect to time. And that is the piece that Maxwell added that makes it possible to have light. And the equations are named after Maxwell because he did a lot of work bringing them all together and kind of bringing the crowning touch to the laws of electricity and magnetism. So now we can look at our summary. We did a lot of review here. And as I say, hopefully you've seen all of these in your introductory physics class in the integral. This is called the integral form. There's a differential form, which is more advanced, which you learn in your electromagnetic theory course. But these are covered in the intro course. So if you look at the four equations, these are the laws of electricity and magnetism, and this is the Lorentz force, how charge responds to the fields. This is how the sources and things create the fields, and then this is how a charge responds that's in the vicinity of those fields that experience something like motion. So now we're going to go to M5. M5. We're finished with the Maxwell equations, and now we're going to look at E and M waves. Now let's look at those Maxwell equations once again. And what we're interested in is to be in space, far away from the charges, where you just have the fields. So you have the currents and the charges somewhere, say somewhere here, but then we're going to be over here. This is going to be us, over here, where there are no charges and currents, just the fields. They're called the free space equations, and what you do is you set Q to be 0, and you set the current to be 0, and look how it simplifies. You just have then these two pieces, the free space equations. Let's write these down. These are the shorter versions of the Maxwell equations here, and the ones that have non-zero would be this one here. Mu naught epsilon naught d phi e, it's the electric flux dt. And then here would be E, so that's the Maxwell piece. And then here we're looking at Faraday's law, minus d, the magnetic flux dt. And just to emphasize, we have set Q to be 0 in the Maxwell equations and I to be 0. Now this is the secret of understanding light. Because see what this is saying, and it's good to study equations, like look at them and stare at them and see what they can teach you. This is saying that if you change an electric flux, and you can do that in outer space, you change the electric field. The electric field is going to be changing. That creates a magnetic field. But this then says if the magnetic field is changing, that creates an electric field. So could we possibly here be having a chain reaction? Electric field creates magnetic field and so on. And notice that when you have the flux, the field created is perpendicular to the flux in each case. So that means if you have an electric field that's changing like this is suggesting a magnetic field that's perpendicular to it starts to oscillate, as you oscillate this, and then this creates an electric field, and so on, B and E. And you could call this, if you want, you could just say, this is the magnetic field. Maybe nice to use M, so that we had, because our title is E and M wave, and this is then M, the magnetic field, and then it's going this way. So this would be implying a doubly transverse wave propagating in space. So you're going along this direction, but in other words, the electric field, say here, the magnetic field, say perpendicular. This is what's being suggested. And this, well, I'll use B because physicists always use B for that, all right? And then here is your direction of propagation. That's a lot. there, and this is very deep, and physicists did not understand this for 25 years, really, since the Maxwell equations, because this is saying that light is propagating itself in vacuum. In other words, you don't need this, which they thought there was an ether because you have to have string. If you have string waves, you have to have water. If you have water waves, and they're figuring if you have light waves, you have to have some kind of light material, light medium, which they said must be everywhere, ether. And this is showing you don't need ether. And Einstein is the one that helped, us understand that you don't need ether. All right. That's not the ether in the hospital, by the way. That's another ether, or in the old days would put you out. Okay, so now we're ready to do the E&M wave, and here we're going to use a coordinate system. The coordinate system that you usually see is a x, y, and a z, and they each have their unit vectors, I hat, k hat, and j hat. I'm going to orient this so that z is down there, and I'm going to, pull the y over around, and then x is going to pop up like here. I just like to do it this way. And here, notice that the very important right-handed coordinate system that's set up where I cross j is equal to k. If you take the I and get underneath, go downstairs, and this is like this to be the ceiling from downstairs, you turn this I into j, your screwdriver advances up. So you can use your right hand. I use the screwdriver that you're just turning. I'm down below. This is like the ceiling. I'm down below, and I'm turning this into j, and my screwdriver advances upward. Okay, so then what I will set up here is we'll look at a situation where we're going to start out here with an electric field, and the electric field, we're going to set up the electric field to be in the x direction. So there'll be an electric field. Here's how I'm going to set things up and see where it leads me. So I have the electric field that is going to be like some E, and then you could say it is an I hat because it's pointing upward. And I'm going to pick the magnetic field to be this way for a specific case to analyze, because that's going to give me a flux through there. So I'm going to pick then B to be some magnetic field along the J direction. So this would be delta X, going that way, and delta Z for the little patch of area. So then if I look at the equation, E with the dl, and set that up, and I'm going to go, use the rule that the magnetic field is this way. I stick my thumb that way, and I'm going to then do the loop that corresponds to where my fingers are curved. So that would be a counterclockwise one here. And for the counterclockwise one here, this E on this other side would be an E plus a delta E, because we're a little bit to the right here. So that's going to give us E plus delta E, the one on the right, and we're going to multiply by delta X, because that's along the path, delta X. And then when we come to the other side, the E is pointing the wrong way, so we have a minus sign, and that would be then E times the delta X on the other side. Here, I don't have any electric field in that direction. So if I did the dot product of the electric field that's in the X direction with this, it's a 90-degree angle, and the dot product going to get you 0. All right. Of course, remember your dot product from your intro physics class. You take A, B, and you want the here cosine of theta. So if they're perpendicular, you get 0. Okay, so when I look at this, I get some cancellation going on. I'm going to get here just the delta E times the delta X. And that delta E, that's moving along the Z direction, so we can look at that as a partial of E with respect to Z times a delta Z. All right, because you have a function here, go delta Z down the road, then the derivative with respect to z delta z gives you that delta E. But now this is interesting because see, this is the area of that little patch there. And according to the law here, Faraday's law, this has to also equal minus the flux, change, the magnetic flux change. And the magnetic flux change here is going to be the magnetic field, which points in that y direction times the area. And that's going to be here, and I go ahead and use partial derivatives since the B has functions of x. Both of these fields have functions of x, y, z, space and time. So this will be the partial, and there'll be a minus sign, and there'll be an A. Now this A here will cancel that A, and I'll have these two being equal. So that means here I have the partial of E. I'm going to emphasize that this E is in the x direction. So let's just emphasize that. E is in the x direction. And so like the magnitude that's hitting that I, it's in the x direction. So just to emphasize that with respect to Z is equal to minus. And since the B is in the y direction, we will emphasize that. So here you have the result that a changing magnetic field sets up an electric field gradient. All right, there's a derivative there. So then we go ahead and consider the next formula, which is the one with the B, and that's going to be E equal to mu naught epsilon naught. All right, it's the same. We're going to do the same thing now, but here we're looking at, okay, this is our Y. We're looking at, with the B, we're going to be looking at down here where your B, points along Y. And here, this is going to be your B plus delta B. And here is a delta Z. And now we have a delta Y this way. And the electric field, remember, electric field points in the x direction. So here is the setup. And we're going to do the same thing we just did earlier. So since the electric field points up, we want to do the loop integral this way, going around that way, counterclockwise. And that would be, here we're going against the grain. So therefore, when we set this up, we have, well, let's do this one first. That's with the grain. So we have B delta Y. And then when we go here, the B is perpendicular, so the dot product is 0. And then we're going to subtract, we're going against the grain, B plus delta B. Now, this was my pilot talk at Middlebury College when I was asked to give a talk and applying for a job. And this is in the introductory physics course. And hopefully you got this far because they do optics in there also. And you have seen this. And I am actually this class is a lot of review from that perspective. And I want to do that because I don't know for sure if you were sick that day and maybe missed some things. I want to make sure everything's covered. So we're doing that to cover all the bases. So if we look at this, we see here that we're going to have a cancellation again. This is going to cancel there. You're going to have minus delta B, delta Y. But once again, this is the partial of B with respect to Z times that delta Z. Same trick we did before. And this is going to be delta Z, delta Y is our area, our patch of area. And then when we apply the equation here, this side here is mu naught epsilon naught. This is d dt of the electric field, see, that's piercing through that area. All right, so that is going to give us mu naught epsilon naught. A will pop out, and I'll have the partial derivative, and just to emphasize, that's an x. and that's going to be dt. Just to emphasize, this is a by. So when we look at this and set these equal, this is going to cancel, and we're going to get the equation here that minus dby dz, that's this piece there, is equal to the other piece, mu naught epsilon naught partial of Vx with respect to t. And that's the second big discovery, the two derived equations. And now comes the fun part. Since the wave equation we know is a second derivative, we're going to take a derivative again. So this is doing like pure theoretical physics. We start with the Maxwell equations. We looked at the free space Maxwell equations, and now we're deriving the wave equation. That they're electromagnetic waves. So if you take here the second derivative of the Ex with respect to Z, then this will be d dz of the dby dt, and the partial derivatives, x, y, z, t, these are all independent coordinates. So we're going to flip these, and do the z derivative first. And guess what? Look at that. That's amazing. In fact, even that sign there, you're going to get some signs. But let's go ahead and let's go ahead and substitute it. Let's not get too fast here. We'll just the derivative with the t, and then for this we'll just keep that minus sign here, and then for this here, this is going to be equal to a negative mu naught epsilon naught dx dt. And I think you can see this coming. This is the second derivative in time. We have the second derivative in space. So we're going to have the second derivative in the space, see? And that's going to equal, minus signs are going to cancel. We're going to get mu naught epsilon naught, and this is going to be the second derivative of Ex dt. Wave equation. Wave equation. So let's go ahead and put that axis in there again, the y, the z, and the x. Put our electric field along the x and magnetic field here along the y. And we're traveling this way. Because see, this is a wave equation, the z direction, see, traveling there down the road. And here, remember the wave equation, we set this up. Remember, this has to be 1 over the velocity, because velocity times time is your distance. So this means your velocity here is 1 over the square root. I'll put the epsilon first, E&M. Electromagnetic wave. And then we plug in numbers, and if we plug in the numbers, as we do in the text, when you plug in numbers for these, you get for the velocity, you get 2, and these are the best known numbers of today. You get this number, meters per second. And if you look at the speed of light, this is insane. It's the same thing. It's the same thing. Light is an electromagnetic wave. A coincidence? 9 significant figures? No, I don't think so. And they have defined in 1983 the meter, which was, originally right after the French Revolution, like 1790s, right around that time, as some bar that was in France, some standard bar size. But now they tweaked the definition slightly many significant figures out so that the meter is defined so that the speed of light is exactly this. So now you don't need the bar. You just get a laser out or something and measure time, do some measurements, and you can reproduce the exact meter anywhere in the world, rather than just compare to some, you know, bar in a museum and then make replicas. So here's a nice picture of the wave. Here, electromagnetic wave, where your electric field is your blue and your magnetic, your red. So traveling to the right. And because the Maxwell equations lead to light, they have these neat t-shirts. And God said, and they're the Maxwell equations, and there was light. There's the brother, engineering major, sister, astrophysics major, and baby, undecided. So here, if you want to create light, you need to have the Maxwell equations come into existence. So that's a very profound statement there, that the Maxwell equations bring in light. Okay, I want to show you now, since you've worked real hard with me on this more complicated stuff, is I'm going to make the numbers simple for measuring the speed of light. And this is going to be light speed measured. And we go to the experimentalist, and brilliant experimentalist, one that became an example of the United States' first Nobel Prize, and that's Albert Michaelson. Born in Poland, came to the United States and then attended the U.S. Naval Academy in Maryland. Got the Nobel Prize in 1907, and he was born close to the middle of the 1800s, but he got married again when he was almost 50, and had children then, and one, Dorothy, I got to meet her. She came to Greensboro in 1979 when I first started teaching at University of North Carolina, Asheville, and she was talking about her daddy and Einstein and telling stories, and had a book written about her dad. And after I gave a presentation, I was so glad that she had come to my presentation. She came up to me excitedly and says, "I want to take your course." I gave a presentation on my liberal arts optics course. And, today she could, because of the online. So this experiment I want to tell you about, Michaelson, has an 8-sided mirror, and the light hits this mirror, and as it travels through a mountain, like 22 miles away, as this turns 1/8, it catches the mirror just right, goes into a telescope, and you can see it. So I make the numbers a little simpler for my liberal arts students that are non-science majors, and we're going to work in the kilometers. So it's 5-kilometer round trip. So Michaelson was looking at 22 miles. And if you do, it's actually not exactly 22 miles. If you go, it was a round trip was not 44. It was more like 47. All right. So this is very close to 75 kilometers. I'm going to use 75 kilometers. And his mirror rotated very rapidly, like 535 times a second. And I'm going to make that 500 times a second. So if we do that, then we have the distance for the round trip is 75 kilometers. And the time for the round trip is going to be 1/8 of a turn. And we're going 500 times a second. So that means here it's going to take a 500th of a second for the mirror to go all the way around, but you'll need to go 1/8. So this is 1/4000th of a second. That's cool. And then for the speed, you need the distance. You need the distance divided by the time, which should be 75 kilometers over 1/4000 seconds. See? And then, as my 5th grade teacher, Mrs. Corsi, taught me, you divide by a fraction, keep, change, invert. So if we do that, and I like to show my students the beautiful mathematics that you can multiply in any order. And when you work this out like this, 4 times 25 is 100, and then you get 300,000 kilometers per second. And if you look at this, this is meters. So if you want kilometers, you're looking at these. But if you look at that, that rounds off, look at that, that rounds off to 300, you know. If you want like 3 significant figures, actually, that's it. So you get it. Very nice. And a student later wrote me, who had taken my class, had gone to the Naval Academy and saw the nice plaque. There's a nice plaque there. And they've changed things around since many years ago when he was there. Okay, so let's look at M7, the light wave. And what I would like to do is write down for the electric wave sign, we're going in the Z direction. All right, like this. And then the B is in the Y direction. So we'll do this. And you could add a phase in there just to play it safe. And then when you take the derivative of the X with respect to Z, which we did, that has to be minus by dt. That's one of the equations that we had done earlier. Let me just look up here. Here it is. And if you do that, the derivative here on the E is going to give you K E naught, and you go with the cosine, KZ minus omega t. So we're taking derivative here with respect to Z. We get the cosine, and then the K pops out. And that has to equal the derivative on this one with the minus sign. And here, if we have the minus sign, we'll have minus B naught. And all of a sudden here, what you get the cosine with the minus omega popping out. So that's cosine. Okay, so let's look at this. This is going to cancel here. Now, for this to be true all the time, we can't have like the Z, you know, messing things up and the Z. So what happens here to make this happen all the time? Phase is 0, then this looks exactly the same. It's going to balance, and then this needs to work here at the front. In other words, K E naught has to be omega B naught. So that means E naught is omega over K B naught. And that has to be, well, omega over K. Remember, that's your velocity in our wave physics. So we get this very interesting result that the E naught divided by the B naught is related by C. All right? Important conclusion. And now we come to our last section, M8. The electromagnetic spectrum, which is our dessert. Because now we can enjoy the richness of the electromagnetic spectrum as we look at, remember the formula C, the speed of the wave is lambda times f, and now look at the rich variety in the spectrum. If you put the wavelength increasing to the right, here you have the size of UNCA, radio waves, the mountains and the valleys of strength, the electric field. And that's a million times a second. This is your hertz. And as you increase the wavelength this way, the frequency and the energy, you may remember from your intro class, the Planck constant times the frequency is the energy of a photon. More about that later. And then here, if you go to, say, the size of a marble, you have microwaves. And as you get smaller wavelength, size of bacteria, you have then, this is, a trillion is 10 to the 12, 10 to the 15 is quadrillion. We just say 10 to the 15 cycles per second or hertz. Wow, it's the visible spectrum. Then ultraviolet, and then the size of an atom, wavelength very short, angstrom. This is X-rays, 10 to the 18 cycles per second. And then here, the size of a nucleus, and you have the gamma rays. So that's kind of neat. You have the visible in the center, violet, blue, green, yellow, orange, red. And, some scientists put it the other way around, have the word G-bib. A lot of photography, and I notice like in psychology, they will use the wavelength increasing to the right. It's very, very common in interdisciplinary areas, like the vision, color vision and things. But it's perfectly fine to see it the other way. So there's the visible spectrum. You can't produce the visible spectrum on a computer printout because these are spectral colors, but it's not bad how they look. Light has to go through the prism. And here's a more detailed, version of the spectrum. Very, very, very nice. Such a richness. And it brings me to my colleague, Professor Debbie Gail Mitchell, who has a very innovative way to surprise her students with things. I like to do that also. So what she did, she used makeup to teach the spectrum. And here's a Twitter post, 2018. This chemistry prompts makeup is inspired by spectroscopy. Debbie Gail Mitchell ordered the colors of her eyeshadow by wavelength to teach her students about the spectroscopy, which is the study of how light interacts with matter. And then a quote from the professor, "Hi, I'm a chemistry professor who loves over-the-top makeup. I'm teaching the spectrum today, so seemed appropriate. Colors are ordered by wavelength. Longer wavelength was placed in the inner corner with wavelength decreasing towards outer corner," Professor Mitchell. So we have this very cool mirror symmetry where you start here with the red end, and she's using 4 of the colors of the spectrum. I'm going to go with yellow, green, blue, and violet. So this is energy increasing to the right. So this is frequency increasing, energy increasing, and the wavelength increasing to the left. And it shows here, if you start with the long wavelength, the yellow, then go green, blue, and violet, it's a mirror symmetry. And look, you actually get the order on the left side. If you look at when you do this reversal, going the other way, yellow is going to be on the inside, and then you're going to have green and blue. So you actually have on the left, you start with violet and go in. So that's the increasing the wavelength. That's the violet to red. And then on the other side, you have the reverse. Very nice. Very, very nice demonstration in her chemistry class. And that's, she is at the, she is at the Department of Chemistry and Biochemistry in the University of Denver, Colorado. And her PhD is from the University of Denver in 2013. And here's what she sent me when I emailed her and talked to her about this and got permission to use her materials. She sent me this. She says, look, we got more here. And I really love this example because we talked about the terrain, the landscape of physics in the previous class, and how theoretical physicists and how you as students are going to be able to give a tour of physics. And this is a tour of physics and chemistry, spectroscopy. And we have all kinds of cool things here. And there are 2 pages in my notes that are larger so that you can see this landscape in a little more detail. And notice here we have our friend, the electromagnetic wave. And you got the electric field, the magnetic field, and mentions how they're 90 degrees apart, and talks about all kinds of other stuff. The formula. This is the H times the F. Sometimes you see the notation, for the frequency, this for F. And you have here this formula here is the speed of light is the wavelength times the frequency. So all kinds of neat stuff there. And on the second page, the spectrum oriented with increasing. Oh, I like this. A violet red. I like that. That's the order I kind of like. And she's got that here for us, and it's so compact. All this this landscape. So I encourage you to think this way. In fact, my class today was an example with the review of the E&M that you did in introductory physics to bring together the Maxwell equations. It was sort of doing this kind of a thing. So always stand back and trust your intuition and your ability to see things in your own way.